Hi everyone! Today let's talk about section 1.6, nested quantifiers. Consider the statement. The sum of two positive numbers is greater than 0. For every x and for every y, if x is greater than 0 and y is greater than 0, then the sum of x and y is greater than 0, where the domain of this course is real numbers, Cartesian products with real numbers. Symbolically, we can write x greater than 0 and y greater than 0 implies x plus y is greater than 0. If we let p of x, y denote the expression x greater than 0 and y greater than 0 implies x plus y is greater than 0, then the expression can be written as for all x, for all y, p of xy. And here are more examples. So suppose state in words, we have this. For every real number w, there exists a real number x such that w plus x equals 0. Okay, so for every, that is the symbol. Okay, let's see here. For every real number w, so for every w, so we have this notation. There exists. So there exists is this like e, right? Flip the e over to the left. And there exists a real number x such that w plus x equals 0. Okay? And because w and x, they are real numbers, we know the domain is our Cartesian products with R. Okay. And next, everybody loves someone. So everybody, this is like for all, right? For all x. And so you can see for all x, someone is there exists. So there exists y such that x loves y. So we let L of xy be x loves y, and then we have for all x there is y, and then L of xy. Okay, so this is how we can translate the sentences into logic symbols. Okay, let's look at more examples. Part A is the statement for all x, for all y, x greater than 0 and y greater than 0 implies x plus y equal greater than 0 with the domain R equals true or false. Okay, so let's see whether it's true or false. Because here we have for all x, for all y. If we want to show it true, we need to show that let's say, this guy is p of xy, then we need to show p of xy is true for all x and all y. So if we want to show it's false, we just need to find one x and one y such that p of xy is false. Okay? Alright, let's see. So we have x greater than 0 and we have y greater than 0. Well, you can see we can add those two inequalities together. Then we have x plus y is greater than 0. Okay? Yeah, we can do that if they are all greater equal to, all greater than. Okay? Alright. And then you can see we actually get x plus y is greater than 0. So this statement is actually true for all x. Okay, so this is true. Okay. And we can put here for all x, y, if x is greater than 0 and y is greater than 0, when we add them together, the sum is greater than 0. And this is true. Okay. Next is the statement for all x, for all y, x is greater than 0 and y is less than 0 implies x plus y is not 0, with the domain is R equals R is true or false. So let's see. If we want to show it's true, we have to show this works for all x and all y. If we want to show it is false, then we need to just find an x value and y value such that this guy is false. Well, this guy is false means we want to find an x and y such that x plus y equals 0. Well, we can pick x to be 1. 1 is a real number. And we can pick y equals minus 1. Then x plus y is 1 minus 1 is 0. You see, this is a counterexample which make the proposition false. So now we have find a counterexample. So that's why this statement is false. Okay, so this is a counter example. All right, let's continue. Part C is the statement for all w, there is this x, w plus x equals 0 with the domain as r equals r. True or false? Okay, for all... Okay, so if we want to show it's true, then we actually need to show for every w, for each w, we can find a x value such that w plus x equals 0. Sounds like it. So let's try it. So for all means the w is any arbitrary real number. Okay, so we can try to prove it. Let w be in a real number, okay, be arbitrary. You can also say let w be any real numbers, okay? Then how do we find the x such that w plus x is 0? We can let x be minus w. Well, then minus w is also a real numbers. So w plus x is now w minus w is 0. See, we have showed us for all w, we can find an x. Of course, this x depends on w. Okay, we can find x depends on w such that w plus x equals 0. So now we have proved it. This statement is true. So far, so good, everybody? Okay. And what's the next statement? There exists x for all w plus x is 0. Wow, can you see the difference between part C and part D? Part C means for every w. Okay, so for every w, there is an x. Well, this x depends on w, so we can put in the subscript here. So this x depends on w such that blah 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 happen. Okay, this is for all there exists. Next, there exists for all. If we switch, what does that mean? Well, this guy means there is x such that for all x, for all w, which is a real number, such that w plus x is 0. So you need to find one x values. So it works for all w in R. You want to find one x such that it works for all w in R. Is it possible? Not possible right here, because here we can show it is false. To show it is false, then we can show for every x values there we can always find some w such that w plus x is not 0. Okay, so How do we show it's false? Okay, to show it is false, let me use a different color here. To show it is false, we need to show that for all x values, there is a w such that w plus x is not equal to 0. And why do I come up with this? You can think about this guy. This guy is false. So the negation of it must be true. So negation of it is, remember, negation of the x's for all, there's x for all w. If it's p of x, y, the negation of it is, for all x, there is this w, not p of xy. So that's why we're going to show the negation is true. So for all x, there is this w such that not p. So w plus x is not 0. Okay, so how does that work? Okay, so for each x values, for example, okay, so here's one example. So we can separate into cases. First case is if w is 0, then we can pick, let me see, okay, sorry. Oh, if x is 0, then we can pick w to be 1. Then we have x plus w equals 1, which is not 0. Okay, if x is not equal to 0, you see, when we combine those cases, we have all real numbers. So we have shown this statement for all real numbers, x, okay? So when x is not 0, then we can pick w to be x. Okay, then we can have w plus x is 2x is not 0. Another easier way is we can pick w to be 0. Then x plus w is just x, because x is not 0, so this is not 0. So now we have shown that no matter what x is, okay, we can always find a w. And this w might change. This w might depends on x. So that's why you can see here, when x is 0, we can pick w is 1. We cannot pick w is 0 because it won't work. But when x is not 0, we can pick w is 0. So this w is actually depends on x. Okay, very similar to the previous example. For every w, there is x. So if you see the quantifiers is for all and then their x's, then their x's usually depends on the first variable. Okay. So now we have shown that this guy is true. So the negation, which is our original statement, is false. Okay, everybody? Let's continue. Is the statement there exists x for all y, x times y equals 0, with the domain is our Cartesian product of R. Sometimes people call this guy R2. Yeah. Okay. Let's see here. Okay. There is x for all y, x times y is 0. Is this true? Can we find an x value that xy is 0? It works for all y? Yes. Do you know what it is? Yes, that is the 0, right? So this is true because we can pick x to be 0. So 0, it actually works for all values of y. Then for all y is a real number, x times y is 0 times y is 0. Okay? So to show this statement is true, we just need to find the x values, and it works for all values of y. Okay? And this is exactly like what we did here. We find the x values, it works for all values of the y. Alright, let's continue. Part F is the statement. There is this x, there is this y, x times y equals 10, with the domain is z plus equals z plus, true or false? Okay, to show it is true, so in order to show it's true, we just need to find the x, 1x and 1y, so it works. Okay, and if we want to show it's false, because this is existential quantifier, to show it's false, we have to show that no one works. So, which means for all xy, we need to show xy cannot be 10. Okay, is this true or false? Can we find x and y such that x times y is 10? Yes! We can find 2 times 5 is 10, 1 times 10 is 10, so we can pick, so this is true, we can pick x to be 2, y to be 5, then x times y is 2 times 5 equals 10. So now we have find the x value and the y value such that this works. So this is true. So far so good, everybody? Okay, let's continue. Is the statements there is this x, this is y, x times y equals 11, where x and y are integers, those are greater than 1. Is this true or false? Well, think about the positive. So think about the integer. The integer divisors of 11. Well, 11 is a prime number. So 11 can only be 11 times 1, right? This is the only integer divisors, positive integer divisors. It could be minus 1 and minus 11. Okay? But you can see 11 is greater than 1, but 1 is not greater than 1. So we cannot find x and y such that x times y is 11. So we know this is false. So how do we show it is false? So because this is existential quantifier, we have to show that no numbers greater than 1 works. Okay, so we can say like this: integer divisors of, positive integer divisors of 11s are 1 and 11. And we know this guy is a prime number. Okay? And this is greater than 1, but this guy is not greater than 1. Okay? So we can't find, because those are the only positive integer divisors of 1 and 11. And if they don't work, then we don't have other choices. So we can't find x and y in positive integer and x greater than 1, y greater than 1, such that x times y equals 11. So that's why this statement is false. Okay. Negation. So if P is a propositional function, what will be the negation of for all there exists? Well, remember the not is really like the negative. It flips things. So it flipped the for all, change it to there exists, and it changed the there exists to for all. So it's like, okay, it changed the for all to there exist, and then the next steps, it changed there exists to for all, and then you still have the not P. Okay? And negation for there exists for all, it changed there exists to for all, and then it changed for all to there exist. And then we also have the not P. Okay, so for set, okay, analogy, right? Numbers, we have the negative sign. Okay, it flip inequalities. For sets, we have it's also like a horizontal segment. This is the complement. Okay, if so negative sign, it flip the inequality, right? And then the complement, it flipped union and intersections. And then for logical operations, okay, propositional functions, we have the not. Okay, the not, it flip the and or, it also flipped the for all and there exist. Okay, this is some analogy. Okay. For example, what is this guy? Not, see, this is the exist. Flip it, it become for all x stay there. And this is for all, so we have the exist y, and then not xy, xy less than 0. Okay, what is this guy? Well, this is for all x, there exists y. xy is not, oops, sorry, pressed the wrong button. X and y is not less than 0. It means x and y, x times y, is greater or equal to 0. So this is what we get. So far, so good, everybody? Okay. Alright, so here are the tips. A lot. Okay. So, okay. So, we have two variable x and y, and then in front of x, well, we can have for all or there exists. So there are two choices. For the y, we can also have for all or there exists. There are two choices. That's why we have 4 possibilities. Okay, we have for all x, for all y. So this 4 possibilities is for all x, for all y. For all x, there is this y, there is this x. For all y, there's x, there is a y. Okay, so we have 4 possibilities, and for each possibility to determine whether it's true or false, well, it gives us 8 possibilities, okay? So here are the 8 possibilities. Okay, let me label them 1, 2, 3, 4, 5, 6, 7, 8. Okay, and the method of each of them is a little bit different. Let's go through them, okay? First, to prove for all x, for all y, p of xy is true, where the domain is x Cartesian product with y, you must show that p of xy is true for all values of x and for all values of y. And so you let xy be arbitrary values in x and y, so arbitrary values. And you want to show p of xy is true. So you usually start to prove as we let xy be any, if your domain is R2, you say let xy be any real numbers, or you can say let xy be arbitrary real numbers. We really like the arbitrary, this word. Okay, and then you want to continue to show that p of xy is true. Okay, second, to prove this statement is false, well, then you just need to find one counter example. So you want to find one value of x and one value of y such that this guy is false. So this is a counter example. Okay. Next, to show that for all x there is this y is true, then you must show that for all x, for all x's, there is just a y to make it true. So you start a problem by you let x be arbitrary and then you find one y values, make it true. And usually this y value depends on x. What does that mean? It means maybe sometimes you gotta separate into cases. Depends on your x values, your y in the different cases might change. So it's not the case that you find one y and then it works for all the x's. Okay, it's usually the case is different x, then you might have a different y. Okay. Okay. So next, to prove, oh, I see some typo. I mean to prove. Okay, this is to prove. To prove that for all x, there is this y, such a p of xy is false. What do? Okay, so we want to find the x values such that no y can make it true. Okay, so, yeah, you have to search couple x values and see which one works. So you want to find the x value, no y values work in this case. Okay, next, to prove there exists x for all y, p of xy is true, you must show that there's at least one xy. So you want to find the value of x such that p of xy is true for all values of y. So you want to find an x values, it works for all values. So y is arbitrary element and you want to find one x values and it works for all y. Do you see the difference between this guy and this guy? That guy is for each x values. So this guy, for each x values, we can find a y, and the y might change. We can have different y. Okay? And then however, this guy, you're looking for one x values, it works for all. Okay? Alright, let's continue. Number 6. To prove there is this x for all y, p of xy is false. Well, you must show that for all x, there is this y value such that p of xy is false. So we let x be arbitrary. So usually when you see, you can also think it this way. You want to show this as false, right? Which means you want to show the negation is true. Well, the negation is, for all x, there is this y, not p of xy is true. Okay? So, that's why you want to show for all x, there is this a y value such that p of xy is false. Okay, so we let x be arbitrary and then we want to find a y value such as to make p of xy false. And usually this y value also depends on x. Usually, okay, it might happen that you can find one y, it works for all, but so in this case, it's good. Okay. Next, 7. To prove that there is this x, there is this y, such that p of xy is true, you just need to find one value of x and one value of y such that p of x is true. Okay, so we just find an example. So we find an example here. Number 8, to prove that there is this x, there is this y, p of xy is false, where the domain is x Cartesian product with y, you must show that p of xy is false for all values of x and for all values of y. So we let x and y be arbitrary elements and we want to show p of xy is false. Okay, yes, that is the 8 possibilities. So yeah, I know if you just see this for the first time, you might need more time to compare because, well, a lot of math symbol and the order really matters, right? So yeah, take more time to, do more examples, and, sometimes it's good to, compare. When you compare different examples, then you can, understand, like, if you can find the similarities and you can find the differences, and then when you have confusions, you read more and do more examples, and then you can solve the confusions. Of course, please, when you have a confusions, let me know. Email me or, ask me in class or ask me in my office hours. So please, when you have a confusion, don't wait. Okay? It's good to solve that confusion right away when you have it. So, and also when you listen to, when you watch the videos, and it's very important to take notes, because when you take notes, you can put down the things you understand. If you don't understand, please put a question mark next to the problem and come to see me. I'm very happy to help you. Sometimes, if I talk to you and then I know which parts you get confused, and then I can explain to you better. Okay, and that is session 1.6. Now we have finished chapter 1. Okay, next class we will talk about chapter 2. Have a nice day. Bye.